Our next speaker in this session is going to be Dr. Nelson, Mark Nelson, from the University of Vermont, who's going to talk about small blood vessel disease in the brain. Dr. Nelson.
Thank you. Well, thank you very much for the invitation to speak. I'd like today to talk about some of our recent work on small vessel disease in the brain. And here in the talks this morning, I'd like to link the previous talks up with my talk. I'm going to be looking at the small vessels, the penetrating parenchymal arterioles that David Kleinfeld described as the bottlenecks. I think these are the reasons why small vessel disease in the brain occurs in these spots. We're going to look at, we see an early channelopathy-like event in small vessel disease model that involves KV, probably KV 1.5, next talk that was presented. Probably also involves changes in the extracellular matrix and metalloproteases, the next talk. And something else that, coming up later on that I'll show you. So, where do we advance them? So, okay, here we go. Just a little bit of background. I want to give us who we are. We have a program and project grant on small blood vessels in the brain. And we thank the Heart, Lung, Blood Institute for that. Marilyn Cipolla and George Wellman are here today. We also have an international network funded by the Foundation Leduc. And some of the members are here, Mike and Nita Gard, I saw in the back earlier, Frank Ferrasi. This is a network to look at small vessel disease in the brain, including basic scientists and clinicians in Europe. So this has been a wonderful opportunity to look at it. A little bit of background. I'm just trying to get every speaker that's being a person in the audience here. The arteries, which you heard about in the first talk that we look at, the arterioles, penetrate from the brain surface into the brain and are surrounded by astrocytes. And these are the key arterioles that we'll be looking at today. So they're in a unique environment. They're surrounded by astrocytes. So that's something different. So small vessel disease. It progresses silently over many years before becoming clinically symptomatic. It contributes to more than 25% of the strokes. You heard something about it this morning, as well as from David Kleinfeld. Leading cause of age-related cognitive decline and disability. No specific treatment. Major risk factors are age, which I'm getting there. High blood pressure, I'm working on that. Blood pressure variability, who knows? So our noble and lofty goals of the network are to provide progress on understanding molecular basis, obviously markers and therapeutic targets for small vessel disease, train scientists and clinicians to work together, and this is what this meeting I think is doing beautifully. And really what you've already heard today too, that small vessel disease, like any disease of any organ, is not simply the tissue of the organ, the heart muscle or the brain, but is in fact all of them have to work together. And I was long ago in a neuroscience program at WashU, and we didn't mention blood vessels or glia once. I mean, and if blood vessels were mentioned, it was a stroke, and that was something we didn't really talk about. So I think they come hand in hand from, as you heard from David Kleinfeld, in controlling behavior and may relate to a lot of cognitive disorders. So what do we study? We are using one of the few monogenic causes of small vessel disease as a model. It's a very rare but monogenic disease, and we view this as a lens into the bigger sporadic causes of small vessel disease in the brain. And this model is called CADASIL. About 1 in 100,000 people have it. It's autosomal dominant. It's the most common cause of hereditary small vessel disease of the brain. It often starts with migraine with aura in the patients in their 20s. Microinfarcts, which you heard about, cognitive deficit, motor impairment, and usually early death. And these are caused by mutations in the Notch3 protein in the extracellular domain and substitutions of the normal 6 cysteines and the EGFR repeats that to an odd number. And this leads to what we think is of the extracellular domains of Notch3 clumping together that start a cascade that leads to the pathology over years. And these are some of my coworkers in Europe in the Leduc network that provides some of the clinical evidence. So this has been one of these very frustrating things where the gene has been known for years, nothing can be done, and fortunately recently there's been a mouse model developed which I think is starting to provide some insights. This, also should mention, Notch3 is expressed only in the vascular smooth muscle and pericytes in the brain. And so remember, it's the extracellular domain sticking out, and the next cell it sees is our astrocyte end foot. So keep that in mind, although we're still sort of at early days. These are some of the techniques that we bring to bear in the rodent models for anything from isolated cells from the arterioles, proteomics. As you heard on the last talk, pressurized arterioles. These arterioles are 20 microns in diameter from mouse. EM, brain slices, and in vivo work as well. This just gives you one of the new tools we have. We have also, this is a calcium biosensor, genetically encoded calcium biosensor. This is a parenchymal arteriole, 20 microns in diameter. This is a ratiometric calcium indicator, and you can just see we're adding a KV channel blocker, and it constricts and calcium goes up. And you can see nicely the smooth muscle cells as they penetrate into the brain to go to the terminal arteriole. I think models like this will be very valuable in understanding what goes on in small blood vessels in any tissue. We also have a similar endothelial mouse. Our European colleagues also try to take the information, we try to bidirectionally and take not only proteomics from autopsies for deposits from CADASIL patients, but also there's a number of genome-wide association studies going on in Europe on CADASIL patients and patients with sporadic small vessel disease. So here are some concepts, and I think will resonate with people, the talks you heard this morning. These are things we're just, I'll throw out to you for food for thought. We're proposing that the mutated extracellular domain of the Notch3 changes the dynamic landscape of protein accumulation extracellular matrix to alter smooth muscle cell function and astrocyte function. That there are dynamic changes, which you heard about from Jerry in the last talk, in the composition of the extracellular matrix between the smooth muscle over time, and we think that some of these changes are common denominators and perhaps in a broader sense of small vessel disease. And one of the ones I'll focus on is changes in metalloprotease activity and the level of the number of KV 1.5 channels in smooth muscle cells as being an early defect in small vessel disease in this CADASIL mouse model. So we use a mouse model developed by Andrew Tellem, a European collaborator, and was described recently in Journal of Clinical Investigation. It's a mouse model that expresses one of the human mutations for CADASIL, R169C. The mouse was developed overexpressing the normal transgene fourfold and the mutant transgene fourfold. And this mouse then developed some of the salient preclinical features of CADASIL, including white matter lesions at over the age of a year. But one of the interesting things is what happens early in the disease process. And I think we're all interested in trying to understand the early changes. And they could be a lot more subtle. It can be because we induce a microclot, or they could be something as subtle as a small change in how the vessel reacts to pressure, which is what I like to propose today. And these things could happen early. They may have long-term consequences. And Anne in her paper showed that pressure-induced constrictions are reduced in the big arteries, the PL arteries in the brain at 6 months of age. This is at least 6 months before the onset of white matter lesions. And whisker-induced blood flow is also reduced. So we wanted to look at the arterioles within the brain, and this shows one of our micrographs where you can see that this moment the arteriole penetrates in the brain is encased by acidic processes, and the red staining is aquaporin 4 for the end feet, and this is the middle cerebral artery. So this shows the basic study you saw in the sort of the Baylis effect, increasing intravascular pressure on a cannulated 20 micron diameter parenchymal arteriole from a mouse brain. And what you can clearly see here is that the blood vessel constricts to pressure in black, and the CADASIL mouse arteriole constricts the same amount at 20 millimeters of mercury, but at higher pressure, 40 being probably physiological for this part of the circulation, constricts about half of what the wild type does. So what this says, this looks like what Anne saw in the PL arteries, but this says a fundamental part of the process, how the blood vessel senses voltage, pressure, is altered in this model of CADASIL. But it's not altered at lower pressures, only at higher pressures. So it's something that kicks in at higher pressures. And what I want to convince you of, what happened, this difference is due to an upregulation of one of the brakes on contraction, upregulation of the KV, voltage-dependent potassium channels. You upregulate a brake on the pressure-induced depolarization, you break contraction. And so this happens at least 6 months before white matter lesions. But I should say the extracellular domain aggregates are detected within a couple months of birth of the animal, as well as the deposits around the arterioles. CADASIL and small vessel disease, CADASIL is a disease of the brain, yet the deposits are found everywhere, and the mutations in all vascular smooth muscle. So we looked at the mesenteric arteries and looked at the same properties. And just to make a longer story brief, the mesenteric arteries, there was no effect of the mutation on any of the properties we could detect in the mesenteric arteries, yet they have mutated Notch3 and they have gum deposits. So we then went back to one of my colleagues, George Well and Messiah Cody are here, and they had shown a couple years ago that in a subarachnoid hemorrhage model, that instead of the arteries constricting less to pressure, they constricted more. And this entire difference was due to a downregulation of voltage-dependent potassium channels, and just the channel number. It looked like there was increased endocytosis. And they showed that, this shows that one of their curves, and so we thought there might be parallels here, that they showed a downregulation of KB channels. So we also looked at KB channels in the arterial myocytes from these arterioles. And what you can see here, control, large increase in the current density of voltage-dependent, probably KB 1.5 channels in the catastral arterioles, which would mean a bigger break on constriction. And analyzing the currents indicated that it wasn't a change in the properties, it was a change in the number of channels. And George and Messiah over here, their work showed 4 days after introducing subarachnoid hemorrhage blood, there was a downregulation of the same channel by endocytosis. So we thought this is an interesting parallel. So this says that the KV channels have to be, their numbers critical for how the artery responds to pressure, depolarization, and they're the brake on it. You change the number, you change the set point. So then this sort of gives a cartoon of it. So the idea is pressure causes membrane depolarization. And the example is previously published that you have a decrease in the number of channels, more depolarization, more constriction. And what we see is an increase in the number of channels, less constriction, and less depolarization. Both can be bad because it means the arterioles are sensing pressure in very different ways and inappropriate ways. And their study suggested that it was metalloprotease activity, an increased metalloprotease activity that led to the decrease in channels. So these show an artery from Anne where these deposits around the arteriole. And so we thought, well, so Anne started investigating. This is how science comes together. And she found one of the proteins that was concentrated in the deposits caused by the mutant Notch3 was an MMP inhibitor, metalloprotease inhibitor, TIMP3, both in deposits from human and the mouse model, making us feel more comfortable about both, I guess, certainly about the mouse. So we have a situation here where downregulation of subarachnoid hemorrhage increased MMP activity. In CADASIL, upregulation increased MMP inhibitor. So what we did separately, we increased MMP activity in these arteries in the way George Wellman did by adding something that would increase MMP activity, or the downstream product of it. And Andrew Tell decreased TIM3 activity, MMP inhibitor. In both cases, we're able to restore normal myogenic tone. So a fundamental question becomes, what happens when you can correct the deficit early on in the pathology? How does this contribute to the overall pathology? And so take-home message, small vessel disease channelopathy, because of the change in number, not properties, is a regulation of the number of voltage-dependent KV channels in the smooth muscle cells. Probably KV 1.5. This is determined by metalloprotease activity, which is dynamically, and this process dynamically determines blood responses to blood pressure fluctuations. Too many channels are not good, and too few are not good, may be pathological. And so I had this made up in one slide. Challenges the study of small vessel disease of the brain. And this is really, you could put it for a lot of things. Requires a spectrum of diverse scientists and clinicians. That's why we're here today. That's what, and our Leduc network and our appropriate PPG make this possible. In the brain and any tissue, it's a unique environment, which you've heard about, in this case encased by astrocytic processes. So we have to think about how the astrocytes change, and particularly their end feet. You'll hear from Mike and Niedergaard later on that there's a flow of fluid right down through these cells that can change extracellular matrix, could potentially change extracellular matrix. I think it's critical to have the appropriate mouse models for disease processes, because we really didn't have anything for humans in small vessel disease. Appropriately genetic encoded biosensors are key, because otherwise putting fluorescent dyes and other things are impossible unless you have them in the right cell type. There's also difficulties in adapting molecular imaging techniques to the mouse microcirculation, which I think have been largely overcome. I think it's important in all these tissues to isolate Let me go. I know it's in isolation, but you also should do the brain arterioles as well, or the arterioles from the tissue bed of interest and the dissociated cells. Culture is an issue. And we need a critical mass of scientific information expertise. Linking up rare Mendelian disorders with sporadic small vessel disease is a key thing. And I would suggest that early functional changes may be very important for the long-term pathology. I'd like to thank all the sponsors and supporters, particularly the Heart, Lung, Blood Institute. George is here. This is subarachnoid hemorrhage people. Collaborators in Europe, Fabrice did most of his work, View from Our Window, and Jutel, her postdoc. Any of the really heavy clinical questions, don't ask me. And here's the lab. All disclaimer ahead of time. Okay, stop my stopwatch, sorry.
Good. All right, open for questions.
Yes, so I have a question. So what do you think notch signaling is transcribing?
I don't, our current hypothesis, it's really the accumulation of the extracellular domain that then oligomerizes and then accumulates other proteins and changes the landscape. So it's not the transcriptional activity per se, but it is, and it's not really maybe the deposit, but how it changes in a dynamic way, as we heard from the previous talk, extracellular matrix proteins. So it would be the notch-free extracellular domain cascade hypothesis.
I mean, that's fine, but notch is still regulates transcription, and so could one argue that notch is regulating a transcription of a mechanical sensor and thereby influencing
it could,
the
and the interesting thing, when Ann Jutel came first to discuss this program with me, she said KV 1.5 is a target. And I said, why? Because Notch3 intracellular domain is a transcriptional regulator in KV 1.5. Because I told her it's KV 1.5 because the arteries don't constrict. And by the way, 4AP also normalizes the differences. So we were looking at it physiological, and she was looking at it genetically. However, it does regulate trafficking, and I think the trafficking is a big issue, a big component of it. Hey, Bob.
Bob Bryan, Baylor College of Medicine. Nice talk, Mark. So with this lack of break, the arterioles and acatocil mice are probably going to have a different structure, so that the lumen, or what about lumen size? What I'm thinking about getting to is the pressure in the capillaries.
Yeah, that's a really good question. I don't know, maybe, but there is some. Anna showed there was some, I get it right, inward remodeling of the peel arteries. The diameter was smaller. We can't say because we never take the same. It's hard to get exactly the same piece of the terminal arteriole. So there are structural changes that go on as well. Would you argue just in face value here that the pressure fluctuations would not be as buffered as well in this model of the arterioles not constricting as much? But I don't know, and I think our network's trying to investigate that.
Jan Kiriaski from Columbia University. Just to follow up on Azrar's question,
Yeah.
We established that Notch regulates MMPs transcriptionally in endothelial cells, and we're seeing similar responses in human brain vascular parasites. We also, I could share with you
Notch3?
Sorry?
Which notch?
Notch3 and Notch1.
Okay.
And in addition, a compound mutant of Notch1 and Notch3 has severe parasite defects early in development in neonates.
Okay.
That includes accumulation of extracellular matrix, excess MMP activity, and in fact we can even see development of GOMs in the brain vascular parasites of neonates. So I think your hypothesis that there's a key extracellular matrix component is correct, but I would suggest that there's certainly a transcription.
Oh, I didn't even mean to suggest there wasn't a. I mean, this. So
I'm just sharing with you a variety of unpublished results on that area.
All right. Well, and so I was hoping somebody in my lab recorded that. So.
Yes. Well, I'll be glad to talk to you.
Okay, great. Thank you.
We're seeing notch regulation of tight junction proteins too. Right there at the junction, the notch regulation of the claudins and the occludin is occurring. So, I mean, you've got notch regulation of not just the basement membrane, but also the proteins at the endothelial cell.
These are all smooth muscle cells.
I
so-
understand, but notch regulation of trafficking is also occurring for those exact proteins that are making up that tight junction. So the
Yeah.
trafficking effect of the notch is real at different points in
Yeah, we haven't looked at it.
endothelium.
I don't think, if I remember correctly, I think at the moment, at least early on, Ann didn't see changes in the blood-brain barrier. But she's looking at it now. Okay, so we got one of our
I just
network
thought I'd
members
bring
there.
that up because
Okay,
it
yeah,
seems
sure.
like a
Yeah.
unifying
absolutely.
concept.
Yeah. I appreciate it. Thanks.
Yeah,
Oh,
just Ariel Gomez again. A comment that I have. Notch3 deficient mice have a poor regulation of blood pressure. They are poorly responsive to vasoconstrictors, and they have an abnormality of the arterioles peripherally.
Yeah,
talking. And I wonder if that doesn't contribute also to the CADASIL in the sense of being hypotensive, compounding the process that you see in
It could. I mean, and this is really Ann Juttel's work, but she has provided, I think, fairly compelling evidence that at least that the Notch3 mutation is not due to a loss of function. And I know there's some discussion about that, but I don't.
But in vivo, they just respond very poorly to vasoconstrictors. I mean, that's
Okay.
very well known now.
All right. Thanks. Thank you very much, everybody.